virtual objects into moving 360 videos. And the work is motivated by the increasing popularity of 360 spherical cameras, especially in entertainment and filmmaking. And it's common to insert computer-generated elements into real video in that application, which is called compositing. But with new camera model, we need to adjust old methods or invent new methods how to do this. Also, we would like to have real-time interaction with inserted objects, which is not possible with a standard approach to compositing, and may find application in very popular recently virtual production, which is visualization of visual effects on film set. So here is the short preview how the final scene will look like. And this is 360 video, but rendered just for the viewer camera. And we can move the object, we can pause the video, move the object. So there are two approaches which are close to ours, which we based on. It's the work of Richardt et al., which used a moving camera. So they calculated structure for motion to get the camera motion, and to do that they tracked on unstaged images. So they needed the video from separate cameras before they were stitched into 360, and that required additional feature matching between these videos. And they didn't estimate the high dynamic range videos, so they used the 360 frames directly for image-based lighting. And unfortunately, the object didn't cast shadows, so they weren't very realistic. There was a second approach, and in the first paper, they used estimation of high dynamic range images to light the objects, and then they extended the pipeline for real-time shadows and user interaction, and it was done in game engine. I think it was Unreal. But all this approach works only for a static camera, so there's no camera movement. So we would like to combine these two approaches to have a pipeline that would work with moving camera and would track features directly on staged equirectangular images. And also we would like to have that estimation of HDR images from standard images for real-time image-based lighting with shadows and also with user interaction at the end. So the first step of our pipeline is to estimate the camera movement, rotation and translation, and the scene reconstruction. And we did our own implementation of structure for motion for that, based on theoretical bits from various literature. So the first step is to track the features, and we use KLT tracker for that, but we modified it to work on equirectangular images. So it tracks features around the image, because this is how the geometry of spherical images work. So you can see when we have one edge of the image, and some of the tracking lines are continued on the right side of the image in this other second square. So when we track the features, then we convert them into a spherical domain in the spherical camera model, and then we apply epipolar geometry for spherical cameras to get translation and rotation between the so far it's just 2 frames, and reconstructed point. And to measure accuracy of reconstruction, we use a reprojection error, but for spherical images it will be a tangential distance on a sphere. So it's the distance between the projection of the reconstructed point and when it was observed on a sphere. Then for every pair, we stack them together in one global coordinate system, so we have just one camera path and all the reconstructed points. And we refine the solution using bundle adjustment, where we use the reprojection error, which is that reprojection tangential distance from the previous slide. And we also use Huber-Law's function to eliminate influence of outliers. And this is the final solution. Here are some results. So on top, we have the original equirectangular frames. Here are perspective projections of part of the image and the different views of reconstructed scenes. So this is perspective, top, and front. So these are reconstructed points. And I don't know if you can see, there's also like a small camera path. Like here, it was a very small circle. Here, the camera was moving along the pavement. And some more results, different scenes. Also, we used a synthetic scene, so it was rendered from fully computer-generated scene to eliminate any stitching errors. So it was pure 360 geometry. So the next step is to stabilize the video, because they were all handheld videos, and we want to rotate every frame, so they are all aligned with a global coordinate system. First, because we want to use it later on for reflection maps, which should be aligned with global coordinate system, and also if we want to stream it in a headset to avoid motion sickness. So to stabilize the video, we just derotate every frame using the rotation we calculated at structure for motion part. And in this example, the camera was moving on the circle looking outwards. And after stabilization, it points in the same direction no matter where it is. Then we apply inverse tone mapping on that stabilized frames, which we then use for lighting. And for inverse tone mapping, we use works of Endo et al., which learns HDR version of an image from low dynamic range version, and we can compare the object lit by two versions of the images. And with HDR, we have more details in shadows, and intensity of light is also different. And then we use reflection maps, a collection of local reflection maps, because we know where the camera was. We have a camera path, so we can sample from the camera path and take the frame from that place and make it a reflection map which is local. And there is a difference, because if we use just one single global environment map, when we place objects in a scene, it doesn't matter where the object is placed, like these two chrome balls, they reflect the objects in the same way. So here's the black car, and it's reflected the same way in both spheres. But if we have a set of local environment maps, object takes reflections from the nearest map, and there is a difference if the ball was further away or closer. Then we want the objects to cast shadows. So for that, we use a technique called differential rendering. And in differential rendering, we have a set of views of the scene. So the background frame. Then we estimate the local scene, which is in this case is a plane fitted to the points we get from structure for motion. And then when we place the object, it casts shadow on a virtual scene. And when we subtract these two and mask out the object, what's left is the shadow. And then we can compose it over the final scene. And this is the formula to do that. And the final compositing is done in Unity game engine, which also provides some tools for user interaction. And here are some frames from the video. There will be also a video showing the results later. So here's the camera moving towards the object, and the object stays in place. And also some other videos, also the synthetic one I mentioned before. But we also can fix the camera and move the object around the scene, and also all the shadows and all the reflections are calculated in real time when the object moves around the scene. So here will be the video to recap the whole pipeline and to present video results at the end. So look at the reflection of the red car on the Buddha. So to sum up, our contributions were an offline structure for motion pipeline that works for 360 videos and with tracking directly on equirectangular images with some sparse reconstruction of the environment. The recovery of spatially varying HDR environment maps for reflections, which we did via inverse tone mapping, and real-time rendering of computer-generated objects into 360 video inside the game engine with dynamic lighting and shadowing and user interaction. Of course, there are some limitations, and they set the direction for future work. So, first of all, tracking is lost close to the poles in equirectangular images because of the high distortion. And moving the tracking from image domain to spherical domain may solve that problem. Also, we have at the moment just sparse scene reconstruction, and we would like to move to do dense scene reconstruction for better environment or local scene estimation, for better shadowing and introducing some occlusions. And also at the moment the light source is inserted manually, but it could be done in automatic way by analyzing the intensity of image pixels. So thank you very much for your attention.
Thank you, Joanna, for the talk. So the last